Thank you for joining today's IEEE Computational Intelligence Society webinar, Evolutionary Multi-Objective Feature Selection. We're delighted to have you with us. I'd like to begin by thanking Ying Bi, Chair of the CIS Webinar Committee, for her leadership in organizing this session, and to express our appreciation to our speaker, Bach, for sharing their expertise with the community today. Before we get started, a few housekeeping notes. Lines will be muted throughout the presentation to ensure clear audio. Please enter questions in the chat box at any time, and we will reserve time at the end for Q&A. The webinar is being recorded and will be posted on the CIS website at cis.ieee.org. It will also be posted on our YouTube channel, and we invite you to stay connected with the Society and learn more about future events by following us on our Facebook, LinkedIn, and Twitter accounts. We will drop those links into the chat shortly so you can click and follow. And now I'll turn it over to Ying to start the webinar.
Hello everyone, it's my great honor to introduce Dr. Bach Nguyen. He's a senior lecturer in artificial intelligence at the University of Wellington. His research focuses mainly on feature selection and construction, evolutionary computation, multi-level learning, and machine learning for climate change and sea level rise modeling. He currently leads several research projects applying AI to environmental and geoscience challenges, including an NBIE Smart Idea project on evolutionary learning for multi-minimal sea level process. Dr. Yuan is the chair of IEEE New Zealand Central Section and previously served as vice chair of the IEEE BD Analytic Technical Committee. He is also the vice chair of the IEEE CIS Task Force on Evolutionary Feature Selection and Construction. So please join me to welcome Bach. Thank you, Bach.
Yeah, thanks you for introducing me to give a talk in CIS webinar. So today I would like to share with you our recent work about evolutionary multi-objective feature selection. Just to confirm that you all see my full screen and my slides up there, right?
Yes, yes.
Awesome, thank you. So for this talk, I will mostly gives you a very basic ideas of feature selection and also evolutionary multi-objective optimization. And then at the end, I will talk about some potential future directions that we can do with evolutionary multi-objective feature selection. And at the end, if you have any question or anything you would like to ask me but not have a chance to talk to me, feel free to send me email through this email address. Then we can talk more about the question. Okay, so let's start from the motivation of feature selection. So we are currently in the era of big data, right? So a lot of data we have many information or characteristics, or sometimes I call feature, to let us to train a machine learning model, right? So for example, we can train a classification, right, to classify whether a patient has cancer or not, and we can base on the patient genes expression to determine whether the patient had cancer or not, right? But the issue here is that sometimes we have a lot of genes, can be thousands or even millions of genes to train our model, and that can lead to a problem which I usually call the curse of dimensionality, where we can't effectively train our model on the high dimensional data. So to illustrate the curse of dimensionality, I usually use this figure here to show you what's the problem. So suppose that we have only one feature. In this case, we have X1 here, and we can split the feature X1 into 3 intervals. Right? And the task here is to classify 9 samples into 3 regions, and the 9 samples are from 3 classes, right? Red, green, and blue. So when we have only one feature X1, on average, we're going to have 3 samples per region, which is good. If we increase the number of features by 1, so now we have 2 features, X1 and X2. And you can see now the number of regions we have is 3 by 3, which is 9. And then the average number of sample per region is only one now. Okay, so it's reduced by 1/3. If we increase the number of features by 1, so we have 3 features with 27 reasons, which means that on average, we're going to have 1/3 sample per reason. So in general, you can see a trend, right? So if we increase the number of features, the number of samples we have on each reason is exponentially decreased. In other words, if we increase the number of features, the amount of data we need to effectively train our machine learning model exponentially increase, right? So normally for that, we may not have enough data for a data set with thousands or even millions number of features, right? And besides that, to store all the data, we're going to need a lot of cost to store data, to process data, to train the model on large amount of data. And because even we have a large amount of sample, we may not have sufficient for thousands or million features, and that can easily lead to the overfitting problem where the model we train cannot generalize well to the unseen data. Okay, so that is the problem we call the curse of dimensionality, right? And also, when the number of features is increased, we mean that the quantity is increased. It doesn't mean that the data quality is increased, because even when we have a large number of features, not all features are useful. Some of them provide noisy information about the learning task, which we call irrelevant features, and some of them are going to provide the same information, which we call redundant features. And of course, you'd like to remove all the irrelevant and redundant features from our task, from our data set, to improve performance, right? We talk more about that later. So what is feature selection? So in general, feature selection is a process of selecting a subset of small features, F prime, from the large feature set, F here, with the expectation that the selected features can achieve similar or even better performance than using all the features here, okay? And the main goal of feature selection is, firstly, to reduce the number of features, so we can reduce the dimensionality of the data. And also, at the same time, we would like to improve the learning performance of the model. And besides that, because we reduce the number of features, and therefore we expect that the model we build on those features is going to be simpler and easier to understand, so make it easier to visualize and explain to other people, right? And also because we use a smaller amount of data, and therefore we can speed up the process of training our model. And finally, because we don't need too much data originally, so we can reduce the cost of getting data. We can also reduce the cost of saving data into the memory. So that is all the beneficial for us to do feature selection. But that, for you to emphasize here, the two main goals of feature selection is to reduce the number of features and to improve the learning performance here. Right. So here you are. So in feature selection, we talk about 3 main types of feature: relevant features, irrelevant features, and redundant features. So let's talk about one example here where you try to distinguish between cats and dogs, a pretty simple classification problem. And suppose that I have 2 features, right? So on this example here, I have feature 1, which is mouth, and feature 2, which is edge, right? Apparently, if you use the feature edge to do the classification between cat and dog, then normally the feature edge cannot do that task very well. And that's what we say, that edge is an irrelevant feature because it doesn't provide any information about the classification task. If we use feature mouth, then apparently you can see that cat and dog have very different mouth, right? So just simply based on mouth feature, we can distinguish between cat and dog. And clearly here you can see, you can draw a line to distinguish between them. And that's going to say that mouth is a relevant feature because it can provide very good information for the classification task. Okay, so that is relevant and irrelevant features. We also have a term called redundant features. Okay, so redundant features mean that the two features provide the same information, right? And we don't need both of them to be in our model. So for example, here, if we try to use tail shape and tail length to do the classification, well, both of them going to have to provide very similar information about cat and dog, and therefore we may not need both of them in our model, and therefore, and normally we can remove one of them to avoid any redundancy we have in the data, right? So in general, for feature selection, we would like to remove irrelevant features and redundant features and only select relevant features to improve the performance, right? However, thing is not that simple. It's not that just removing irrelevant and redundant features. The issue here is that we have also the complex interaction between features, which is sometimes called complementary features, which is when two weakly individual features, when they combine together, can form a very strong combination and provide a lot of information about the classification task. So an example here you can see is that suppose I would like again to classify between cat and dog, right? And I have two features, okay? One is facial expression. It can be angry, it can be happy. Apparently, though this feature is not that strong, we cannot exactly tell whether a face is cat or dog, right? The same thing if we look at, say, the tail behavior, right? It can wave or can be right up, right? We also cannot tell exactly whether the cat or dog based on the tail behavior. So both of them, we say facial expression and tail behavior are individually weak features. However, when we combine them together, facial expression and tail behavior, we can provide very strong combination because we know that for cat, if she or he is angry, then normally her tail is going to be upright. Okay, so if we have angry and tail upright, that is cat. And also when we see an animal, when she is happy and she is going to wave the tails, then that will tell me that's be dog because that is a behavior of dog when she is happy, right? So combining them can clearly tell me which one is cat and which is dog. And that is a complementary between the features. And that interaction is the first and most important challenge that make feature selection very hard to achieve because you're not only going to detect relevant features and redundant features, but also you would like to find the interaction between features. That's where weakly relevant features combined together can form strong combination of the features. And an effective feature selection algorithm should be able to detect such interaction. Some other challenges, including the search space. So imagine that if you have D features originally, then the total number of possible feature subset is 2 to the power of D. So the number of possible combination is increasing exponentially with the number of features. I have a simple example here where I say that suppose a data set have 30 features, right? Then the total number of possible feature subset is 2 to the power of 30, which is this number here. And if I suppose that it takes 1 second to evaluate one feature, then it's going to take about 34 years to find the optimal feature subset from only 30 features, right? Which is about, I think, 10 times of a PhD thesis, right? So you can see only 30 features takes that much time. If you have more, it's going to be much more expensive. And therefore, we need to have an effective search mechanism to explore such large search space. The other issue, and potentially the most important issue we can talk about in this seminar or webinar, is the conflicting between the two main objectives in feature selection. So as I mentioned before, the two main objectives of feature selection is one, to maximize the learning performance, and two, to minimize the number of set of features, right? Apparently, if we select too few features, then we are at risk of losing information, and that's when we're going to reduce accuracy. And when we keep setting more important features, then we may have more information that's going to improve the performance. So there is a trade-off between the classification performance and the number of features that we have to consider during our selection process. And that's why we say that feature selection is a multi-objective problem, right? Okay, so the main focus of today is the use of evolutionary computation, and particularly evolutionary multi-objective optimization for feature selection. So why EC or EMO are so popular nowadays for feature selection? So the first thing is because EC is a population-based search family, which means that during a search, we have a multiple solution going to explore multiple regions in a search space at the same time, and that work particularly well with the problem with large search space like feature selection, because it has potential to return the global optima in large search space, and that's why we could like to use EC and EMO for feature selection. The second one here is that for EC, we normally do not require any domain knowledge to do the optimization process. To say that, in fact, if you do have domain knowledge, it's very easy to inject such domain knowledge into EC search, and it can, by doing that, it can effectively improve the search performance of EC2, right? And the other thing is EC does not require any assumption, especially about the finite function. For example, it doesn't require the finite function to be differentiable. So it's very flexible, and you can use with any kind of learning model. It can be even the separate model where you have to run very expensive simulation to get the finite function, right? And then EC can also very easy to handle constraints. So the most easy way is you can inject a parity into the finite function. So if a solution is not feasible, right, then the finite function of that solution is very bad, and we're going to eliminate that solution in our sub process. So very easy to handle constraint in optimization. And the final and probably the most important one here is that we say that EC they have is a population-based search mechanism, right? It means that we have a lot of candidates going around the search space to explore the search space. And the good thing here is because we have so many solutions, so many candidate solutions, right? So it means that each solution can represent a trade-off between the two competing objectives, and therefore it naturally can be used to solve the multi-objective problem, where the main goal is to find a set, we're going to set up a parallel solution where each solution is going to be different trade-off between the two objective F1 and F2 here, okay? And in EC, EMO is one branch that have all the algorithms that can be used to handle multi-objective problem. And because feature selection is a multi-objective problem, and therefore EMO has been also used a lot for feature selection. Right, so when we talk about applying EC or EMO to any learning problem, the first and foremost two questions that you have to answer is how to represent the problem to EMO, and what are the operative or finite function we're going to use for EMO, right? So for the representation, the most popular one is going to be the vector-based representation. And the idea is quite simple, right? You're going to use a vector with a length equal to the number of features. So for example, here we have 6 features. We're going to have a vector of length 6. And each vector entry going to tell me whether the corresponding feature is selected or not, okay? And for vector base, we have two main ways to do the vector representation. The first one is the binary representation, where each entry is a binary value, so either 0 or 1. 0 means that the feature is removed. 1 means that the feature is selected. So for example, here we see that for this vector, we have 3 features selected, F1, F3, F4, right? And the binary vector representation is mostly used by geodetic algorithms or GIS. We also can use continuous vector representation to for feature selection. So the idea here is each vector entry is going to be between 0 and 1. And to determine whether a feature is selected or not, you're going to compare the entry value with a threshold value, I call theta here. And if the entry value is greater than the theta, it means that the feature is selected. So in this case here, we set the theta is 0.6, right? And then based on the entry values, only 2 features, F2 and F3 are selected. And this continuous representation is mostly used by particle square optimization and differential evolution, right? So that is about the representation. For the objective function, quite simple. We're going to use or minimize the 2 objective function. The first one is we would like to minimize the classification error rate, which is F error here. And we also would like to minimize what they call the selected feature ratio, which is the ratio between the number of selected features and the total number of features we have originally. Okay, so both of them going to be in the range 0 and 1. Okay, so they have the same range, make it easier to optimize. Right, so for EMO-based feature selection, there are 2 ways you can approach it. One is domain-based feature selection, and the other one is decomposition-based feature selection. So let's start from the first one, domain-based feature selection. So what does domain means here? So I give you a very simple example here to explain the term to you. So you can see here, suppose I have an example where I would like to minimize both F1 and F2, right? And we have a 3 solution, A, B, and C, right? If you compare between A and B, right? Apparently, A has smaller F1 value than B, and A also has smaller F2 value than B. So on both F1 and F2, A is better, right? And therefore I say that A dominates B, right? If you compare between A and C, right? Here A and C here. So you can see now in terms of F1, C is better, A is better because A has smaller F1 value than C. However, in terms of F2, right, you can see that F2 here, C has smaller value than A, which means that in this case, I can't tell A and C which one is better or which one dominates the other, because A is better than C in terms of F1 and C is better than A in terms of F2. And in this case, we call them non-dominant solution. Okay, and the overall goal of multi-objective optimization is to find all the non-dominated solutions, which are the solutions that are not dominated by any other solution. And those solutions together can form an approximation of the petal front, or sometimes I call approximated front of the algorithm. And the representative algorithm for domain-based EMO is NSGA2, SPEAR2, and OMO-PSO. The general idea here is the solution or the candidate solution can be ranked based on their dominant power, right? So the more solution dominated by a candidate solution, the higher the rank, and then we're going to rank the solution based on that, and the better one going to be selected to join in the crossover and mutation to produce the next population. Okay, that is general idea of domain-based EMO. So if we apply that to feature selection, this is the first work I think done by my supervisor, Professor Bing Sui, applying OMO-PSO to do feature selection. Okay, and in this work, the most important result is the comparison between multi-objective feature selection and single objective feature selection. So in the figure here, the blue one here, they are all the solution involved by OMO-PSO, so multi-objective optimization. And on the green one here are the best solutions involved by single objective PSO, and we obtain them from multiple runs. Okay. So clearly you can see that if you compare solution achieved by a multi-objective PSO and solution achieved by single objective PSO, we see that the MO as a multi-objective one can select smaller number of features and also with smaller classification error rate compared to the single objective one. So in general, multi-objective feature selection is usually achieve better performance than single objective feature selection, mainly because of the diversity in the population, right? However, we also notice one downside in the front here. You can see that most of the feature subsets are focused on the center of the front. Okay, so we don't have a solution down here with lower error rate, or we don't have a solution a bit up here with a higher number of feature, right? So we try to kind of investigate why we have such problem, and we found two main problems. Okay, the first one is we find that in feature selection we have a lot of duplicated solution in the search space or objective space that makes the diversity of population reduce. Okay, and that's going to lead to less diverse branch. And the other problem is that comparing between the two objectives, reducing the number of features and reducing the error rate here. Normally, reducing number of features is simple, very simple. You can just simply removing the features from the set that can reduce the number of features. However, to reduce the error rate, we have to be very careful about which features we can remove and which feature we can select in a way that we would like to select complementary features, and it's very hard to achieve. And that's why we say that reducing number of features is much easier than reducing error rate. And therefore, as a beginning, EMO seem to focusing on the easier problem, which is to reduce the number of features. And that's why most of the solution focusing on the reason where the number of features is small, without focusing on the reason where the classification error rate is low, right? So let's talk a little bit more about the duplicated issue. So the reason for having too many duplicated solution is because in feature selection we have a lot of redundant features. So just recall, redundant features going to provide the same information about the classification task, right? So it means that if two solutions select two redundant features, right, or they provide the same information about the classification task, and therefore they're going to have same classification performance, right? So for example, here you can see we have a three subset, right? S1, S2, S3. All of them select the same number of features with S2. All of them have the same classification error rate, right? However, if we look into which features are selected, we see that they are setting quite different features. Okay, so S1 select the first two features. I2 select the third and the fifth features. I3 select the first and the fifth feature. So apparently, based on that, you can see that the fifth feature here and the second feature here, they provide the same information about the learning task, or the combination of the third and the fifth could be the same as the combination of the first and the second, right? So because of that, because of random features in EMO-based feature selection, we have so many duplicated solutions in the objective space. So same number of features and same classification error rate. So how can we handle this problem? How can we increase the diversity of our population in the objective space, right? So one way to do that is we can use duplication analysis based method. So the idea here is, instead of looking at the objective space, which is the number of features and the error rate, we're going to look at the feature space. Okay, so we would like to compare the solution not only on the number of features, but also on which features are selected. And we're going to compute the distance between feature subset based on Manhattan distance, right? And then based on that, we can tell whether two features disagree, sorry, two feature subsets disagree on some features, right? So the more difference between one feature subset with other feature subset, we say that that feature subset is, say, more unique, right? And then the dissimilarity here can tell us how unique the solution is, right? And then we can rank the solution or subset based on the dissimilarity between each and then other feature subset. And we're going to select the most different one from the population. And by doing that, we can actually increase the diversity of our population and also increase performance of EMO-based face selection, right? So that's one way to handle duplicated solution in feature selection. The other problem we mentioned is when we say that the two objectives are not equally difficult, right? So reducing number of features is much easier than reducing the classification error rate. And normally for feature selection, we care more about having lower error rate. So somehow we have to guide the search to focus more on the feature subset with low classification error rate, right? Which is a more difficult objective to achieve. So this work done by Ru Wang Zhao, who is a postdoc also in our group. What he did is that he would like, firstly, he want to find all the non-dominated solution in the current population, okay? And then he going to use the solution with the lowest, sorry, the highest error rate here. So we also mean that you should have lowest feature ratio, okay? And he's going to use that as, let's call it an indicator point, okay? And that indicator point here, the 0, 1 here, going to tell me where I should focus on. So what is acceptable classification error rate, okay? And we say that in the suspect here, any solution with higher error rate than the indicator point here, that is not acceptable, and we call them infeasible solution, right? And all the solution with the error rate lower than the indicator point here, that is going to be the feasible solutions, and we're going to focus only on the feasible solutions. So somehow by doing that, we're pushing more pressure and also more computational resources onto the feasible region, which is the region with lower error rate, right? So we are turning from the standard multi-objective problem into a constrained multi-objective problem where the focus is on the region with lower error rate. And you can see that during the evolutionary process, the indicator point can be updated slowly, and that's going to slowly pushing down the line here, making the focus more and more on the reducing the classification error rate, okay? So that's one way to also improve the performance of domain-based feature selection on the region with a low error rate here, okay? So that is domain-based feature selection. We can also use other branch of EMO, which is decomposition-based feature selection, okay? So what is the main idea of decomposition-based feature selection? So the representative algorithm for this branch is multi-objective evolutionary algorithm based on decomposition, and or short, we call them MOEAD, which is a framework for achieving multi-objective solution based on decomposition. So the main idea here is, instead of having to solve the original multi-objective problem, we're going to decompose that into multiple single sub-objective problem, okay? And to do that, for each sub-problem, we're going to define a weight vector. In this case, for example, we have two objective function, f1 and f2, right? So we can define weight vector with two entry values, W1 and W2, to combine the two objectives here together, right? So if we have different weight vectors, we are representing different trade-off between F1 and F2, right? And for each weight vector, the intersection between the search direction of that weight vector and the path front can give me 1 point on the front, okay? So by defining the weight vectors to be diverse, then we are more likely to get more diverse front during the sub process. And that's why normally comparing with domain-based method, the MOED one can produce more diverse front. Okay? So that seems good because the weakness of domain-based feature selection is the front is not diverse. Okay, so the question here is, can we directly apply MOED for feature selection? Unfortunately, the answer is not, and there are several reasons for that. Firstly, if you think of feature selection, we don't have very nice continuous front like this. The front we have in feature selection is actually highly discrete. Okay, so we only have a discrete point here, which represent the number of features and the classification error rate. Okay, so if we don't define the weight vector carefully, for example, for this weight vector, this weight vector doesn't correspond to any Pareto solution. So we are waiting research on that. Okay. And the other problem is we do say that we consider we would like to have a lower error rate, which is more important than having lower classification feature ratio, right? So that is somehow also called the imbalance important between the two objectives, right? So because of that, how we can handle those issues in feature selection. So in this work done by us in 2020, what we do is, instead of using weight vectors to decompose a problem, we are using what we call the reference point to decompose a problem. Okay, so each reference point here will be corresponding to one feature ratio, and it is an idle point because you can see here is lying on the F ratio axis, which means that this point has zero error rate, which is idle. We may not be able to achieve that, but this reference point serves as a target for our candidate solution to be pushed toward the reference point. So for each reference point, we're going to achieve as low error rate as possible. So reduce distance between the candidate solution and the reference point. Okay, and clearly by doing that, each reference point or each subproblem going to give us or give me 1 point on the front. Okay, so we will not be wasting any computational resource for feature selection, and also because we are focusing only on the error rate for each subproblem, so apparently give higher priority towards improving error rate performance. Towards reducing the error rate, right, or improving the classification performance. Okay. Another problem that in feature selection is, although it says that the feature selection is a multi-objective problem, but in fact, I will call it a partially multi-objective problem because the two objectives are partially conflicting. So imagine that we start from the beginning with all the features, with all the irrelevant and random features we have, right? In that case, if we're reducing the number of features, that's when we remove irrelevant and random features, right? And the performance actually improve, okay? And that's when they are not conflicting, okay? That's when reducing number of features actually improve performance. However, if we reach a threshold here, that's when all the irrelevant and random features have been removed. Now, the subset we have are all the important features. If we keep removing features, then now we are losing information. And that's when the performance is reduced. And that is when they become conflicting. Okay, so the task of multi-optive feature selection is not only find the front, but also to find where they are conflicting and focus the search on the conflicting region only. Okay, so I apply the same idea as the previous one in reference point, but now I want to allocate the reference point along different intervals. Okay, and for every certain number of iterations, I would like to compare the solution between the interval, and that's going to tell me. By doing that, that's going to tell me which interval, the two optives are not conflicting anymore, and that's when I say that okay, now focus on the conflicting region only, and allocate all the reference points on the conflicting region and do search space. That's why I call dynamic reference point to find where they conflict and focus on that conflicting region. And we apply the idea to feature selection, and we found that using reference point actually can significantly improve performance over using on the EMO algorithm, and also using dynamic one can even improve performance further than using only static reference point. Okay, and that is the general idea also for using decomposition mechanism for feature selection. Okay. I would like to spend a few 10 more minutes on the issue and challenge because I think it's very important for people to do feature selection correctly. So here is a slide I really like because a lot of people are confusing between two ways to do feature selection. Okay, so I list two methods here. The first one is suppose I have a whole data set. Okay, and then what I do is I'm to apply feature selection. So be selection here. I'm to apply feature selection on the whole data, right? And then after that, after I find which features are important, I'm going to transform the data using only all the set of features and split into training tests, and then test the performance of the set of features by training the learning model on a training set and test the model on test set. Okay, that's one approach. And the other approach is this one here. When I have data set, I'm going to split the data set into two parts: training set and test set. Okay, and then I'm going to perform the feature selection only on the training set. Okay, and then after that, after I get the set of feature based on training set, I'm going to transform the training set and the test set using only set of features, and I can train the model and get performance on the test set. Okay, so those are the two main ways. One is to feature selection first before splitting. The other one is split first and then do feature selection. Okay, I will leave you 1 minute to think about which one is going to be the correct one to do feature selection. All right, so hopefully now you have a rough idea of what is the correct way to do feature selection. So before I answer my question, I want to tell that feature selection is a machine learning problem. And for all the machine learning problem, the overall goal is to learn a knowledge that can be applied to unseen data that coming from future, right? So that's why I say that we focus on the generalization of the learning knowledge, right? So if we do as the first one here, normally we're going to achieve very good performance because we perform feature selection on the whole data, right? And that gives you sometimes like 90%, 100%, even 100% on the performance testing on the test set here. However, the issue here is that we are doing feature selection on the whole data set. And that's sometimes we call feature selection bias. Okay, and that is there's a leakage of data here, and because we select the feature for the current data, it's going to work well for the current data, but we have no way to guarantee that the set of features going to work well for unseen data in the future, right? And that's why this approach is not the correct way to do feature selection. And the second one here, where we have to split first and then do feature selection only on a training set, okay? And then a test set here will never be you during the session process. It only be you, it is only you to evaluate the performance of the set of features, right? So this one can avoid the feature selection bias, and that is correct way to do feature selection. Okay, a few years ago when I finished my PhD, I have been reviewing a lot of papers that doing in this way, that introduce feature selection bias, and which is can give you very high performance, but it's wrong way to do that. Again, when I see any papers doing that, I just reject paper directly. Okay, I see fewer and fewer papers doing this, and nowadays see most people are doing in the correct way, but I still like to go the people here. So the correct way is you have to split first and then do feature selection after splitting. Okay. So that is about different about the correct way to do that. And also I would like to emphasize a little bit more on the future direction we can do for multi-objective feature selection. Okay, so the first one here is of course you can see that for evolutionary multi-objective feature selection, we can evolve a set of non-dominant solution, right? So that's when they have a own the subset with different trade-off between the number of features and the classification average, right? But then the question at the end here is if we would like to select only one single solution from that, then which ones we select? Okay, so that is one question we have to answer if we only get one solution from the front. The other one here is most of the existing multi-objective feature selection, they only perform the crossover and mutation currently based on the objective space. So which solution we're going to select, right? And then we're going to do crossover and mutation on the solution. However, there's somehow a disconnection between the objective space and the solution space. So for example, I'm not so sure that a modification in the solution space can actually lead to an improvement on the objective space if there's a way that we can link the two spaces together in a more meaningful way. So we can have some guidance from objective space to solution space, and so some guidance back from solution space to objective space. That could be more effective search for multi-objective feature selection. And also, as said, right, feature selection is a bit different from other multi-objective problem. That's where the two objectives are not 100% conflicting, they are just partially conflicting, right? So as I said before, it's very important for us to find out which reasons are the conflicting reason, conflicting reason, and we can focus more on that conflicting reasons. Okay, so we have done very initial work on using reference points on finding the conflicting reason, but I believe there going to be more space for more sophisticated method to figure out where are the conflicting reasons and focus more on that reasons. Okay, and the same thing here says that for feature selection, the front is highly discontinuous front, and even for discontinuous front, the solutions sometimes are not evenly distributed in the objective space. Okay, so sometimes we have for some data set we have a solution focusing more on the region with low average. Sometimes we have the solution focusing more on the central of the front. So we have to find a way to automatically find out such a pattern and going to allocate the search resources on those regions. That's going to also improve performance of multi-objective feature reduction. Okay, sorry, feature selection. Okay, and another problem is that even we talk a lot about using splitting between training tests to improve generalization of feature selection, I still find that selecting generalized feature subset is not easy, and we very easy find a fitting problem in feature selection where we select features that fit too well with the training set and the performance on the test set is poor, right? So that happens especially when you're going to use classification model to evaluate the subset. So somehow, beside the splitting train and test, we also need to develop a generalization method and put it into the fitness function to improve the generalization. And or we can consider generalization as one additional objective for feature selection. And the final one here is we talk stability of feature selection. So that is a problem when I face in the real world application when we try to select gene expression for cancer classification. The issue here is when we have a bit more data and we put it in our current data and we perform feature selection, somehow our model going to select completely different feature subset from the original data set. Okay, so we expect that by having a little modification to the data set, we don't expect that the feature we select going to be too different. Okay, they're going to make it, especially for the expertise in that field, they are less confident about our decision. Okay, so developing a stable feature selection mechanism is so important. Okay, and not much work have been done that to improve the stability for feature selection. So one way also is to consider stability as one additional objective for feature selection and put there so that we can select feature with smaller number of features with low average, but also with high stability and improve our confidence in setting those features. And that is very much in my talk today. And I just touched a very basic concept of and the most repetitive method we have done for evolutionary multi-objective feature selection. If you would like to know more details about EMO-based feature selection, I recommend you to have a look at this paper here, this survey paper here, that we will review a lot more EMO works for feature selection in classification. And that's published in TBC 2024. If you would like to know more general about feature selection, you can look at two other survey papers, one focusing more on general EC and then one focusing more on Scrum intelligent approaches. Okay, and by that, I want to conclude my presentation today and happy to take questions from the audience. Thank you.
Thank you, Bach, for your interesting talk on evolutionary multi-objective feature selection. And I think we have several questions in the chat. The first question is about what would be a strategy to automate the process of identifying irrelevant features?
Right. So I mean, that is the whole process of using EMO here. So as you see here, at the beginning, we may not be able to know which features are also. So first one you can do is you can use some kind of, we call the filter measure, right? The filter measure such as mutual information, relief F or correlation, and you can calculate the correlation between the features and the class label. And if you see the score is low, it means that that features may not provide much information about the class label, and that is the most simple way to remove the completely irrelevant features. But normally in feature selection, we don't know that in advance. Sometimes the feature can provide some information, not too much, so the score is not high but also not low. Okay, so in order to automatically do that, we can use that's why we use EC-based feature selection. And during a search mechanism, we evaluate the feature subset, and based on the evaluation, we see which feature combination is good, which feature combination is bad, and we see the bad combination. the suppose set will gradually ignore those combinations and focusing more on the strong combination that can automatically filter out on the irrelevant features and also find out the good combination between the features. Yeah.
The second question, are the two methods applicable to other problems such as regression or clustering? I think it's related to some of your slides.
Two methods. You mean the domain-based and the decomposition-based method, I guess. I mean, I get that. So I would like to say yes. So when I explain feature selection here, they're very general. Okay. So here I just say that the error rate is going to be used as one operative function, but if you are going to apply to regression, feel free to change it to the regression method, for example, R square or root mean square error or mean square error. They can also be the same, do the same thing, and you can apply both domain-based and MOED simply on regression for feature selection. Yeah.
Next question, how do you consider feature interaction?
Right. So as I just explained in the first question, so that is very important question we had to answer, but that is very hard to know. So the one way we had to do that is based on the evaluation, especially the classification performance here, right? So if we see that the classification performance is high, then it's likely that the comparison of the feature is good. So those are complementary features. If we see the performance is low, it means that the combination is not that good, so we should not combine those features together. And during the evolutionary process, we expect that the performance of the best solution going to be improved over time. And given that, then the best solution evolved by EC going to tell me what is potentially the best combination of the features or the best complementary features.
Next question about the multi-objective formulation. In addition to the two objectives, the error rate minimization and the minimization of the number of the selected features, what objectives has been studied in the field of multi-objective feature selection? Are there any studies on many objective feature selection?
Many objective. I don't think I have seen papers doing many objective feature selection. I have seen some paper working on stability. So they develop the new stability measure to make sure that if we have different split between inside a training set, we expect the feature success should not be too much different, and stability has been included in the as one objective in feature selection. So that is still, I think, 2 + 1 is still 3. So they still call that multi-objective problem. But if we have more than 3, then that's going to be moving to many objective problem. But I have not seen work so far on applying.
So I have a follow-up question. How do you measure the stability in
Right.
feature selection?
Yeah, I didn't put in detail here, but so when we do feature selection, we split into training tests, right? And we have a training set here, right? So when we evaluate a training set, I think that from different generation, the author have a different split of training sets, okay, for qualification. And they could compare the two different splits to see whether the features are the subset are different or not, and based on the difference between the two subsets, and we can tell how stable the algorithm is, I think. Yeah.
So this is related to what the feature are selected, not the accuracy or the training accuracy and performance.
Yeah. So we expect that if we have small difference between the training set, we don't want to see so much difference in terms of the set of features. Yeah. So exactly what feature I said. Yeah.
Yeah. Next question about the multimodal multi-objective optimization. Is it important to find a number of different subsets which are mapped to the same point on the paletal front in the objective space? If it is important, could you please explain why it is important to find a number of different feature subsets within the same performance in the objective space?
Yeah, I think that is an interesting and very important question. So to my point of view, multimodal feature selection is interesting in two ways. Firstly, for multimodal, what I see is that after running feature selection, we may get multiple solutions with the same performance, right? So by looking at the feature subset, I can see which two features are equivalent. And why it's important is because sometimes in practice, some features are very easy to collect, but some features are very hard to collect and very expensive to collect. If somehow the two features have or two feature subset have the same performance, right? However, one feature subset is very easy to collect, then wow, that is what I would like to achieve, right? So I would like to use that feature subset instead use the other one which is more expensive to get, right? So I think that is one of the advantage of doing multimodal. And the other one here is because we can see multiple solutions with the same performance. So somehow by doing that, I can also analyze the interaction between features, whether they are redundant, where the two features are very important to be set together and that appear multiple times in the multimodal solution, right? So that also tell me the interaction between feature, complementary features and also redundant features. So those are the two main motivation for me, I think, to do multimodal feature selection.
But how do you think about the multimodal, multi-objective feature selection? Because
Oh,
the situation may be more complex when
yeah, I
the
think that
object
is going to be more complex. So that's going to solve two problems at the same time. But I think that is so equivalent important. So that is when you still would like to find the same feature subset, not the same, but the different feature subset with the same performance. But also you can give different share between the number of features and the classification performance. And that I think is going to give more choice to the users. Okay, not only about which features are cheap to collect, but also on what is the best trade-off you would like to have between the performance and the number of features. Yeah.
Next question. Thanks for your presentation. What dimensionality was used to test this approach? Large dataset or a small one?
Can you repeat the question?
What dimensionality was used to test this approach? Something related to your dataset. Yeah. The
Right.
dimension of your dataset.
That's a good question. I think I have seen papers that testing multi-objective feature selection on 15,000 features with about a few hundred samples, more on gene expression data. I also have seen papers working on feature selection on dataset with 10,000 samples, but only with 32 features. So it's very diverse between the number of features and the number of samples we have in the current data is used for EMO-based feature selection. Yeah.
Mhm. I think the next question, probably also the last question. Thank you for your explanation. I would like to ask for your views on multitask, multi-objective feature selection. What are your perspectives? Or
Multitask, so many multi.
yes,
All right.
kind of
Multitask.
a little bit of popular topic in recent years, right?
Yeah. Multitask. So I actually I have seen people doing multitask feature selection, but have not seen multitask multi-objective. But let me touch the multitask first. So I think for multitask, there are several advantages of doing multitask. First one is because I think the original feature selection is quite complex, especially the search space. So several people doing many tasks, for example, so you can start from the original task, and they're going to define other tasks smaller, which contains only small number of strong features. Okay, and we expect that searching on the small space going to give us some knowledge about the combination of the feature, and you can transfer that knowledge to the original task, which is working on much larger search space. And that's one way to do multitask feature selection to improve the performance. The other one is I think some people also do similar thing as MOAD, where each task is going to have a different way to form the feature subset, or sorry, to form the finish function, or sometimes I think we call multi-form feature selection. So different form going to have different sub problem, and they have to have different share between the number of features, and they have the sub population for that form. And I think the main reason for doing that is they need to have a different a higher diversity for each subpopulation, and therefore they combine them together. That's going to also improve performance of feature selection, I think. So multitask, I think, is interesting objective, but still, sorry, interesting idea. But still, the question here is how you can form the meaningful task for feature selection, and how you can ensure that even when you form the task, you will not lose any interesting combination between the features from the original set, right? And then we combine multitask and multi-objective. I think they two work in for different purpose, right? For me, multitask is more on making the problem easier, and multi-objective is more on finding multiple solutions for multi-objective, and they can work together so that they can make the search easier, and also at the same time can still find multiple tier of solution between the number of features and the classification average, I think. Yeah.
Okay, I think because now we are getting the time, and I would like to thanks back again for your great talk on feature selection. Thank you, and also thanks all the attendees for your attending. And later you can access the webinar, the slides in the IEEE CIS archived webinar, the web page. Thank you all, and
thank you.
that's all. Yeah, thank you.
Bye-bye.
Bye bye. Good night, back.